Hello, this is the lecture series of physical chemistry from Soli Gloria University Church. So Soli Gloria, physical chemistry. These topics are about molecular symmetry. So we are going to talk about symmetry element and their operations. And there are a number of symmetry elements belong to a particular molecule. And all of those symmetry elements shares a common point. So that group of symmetry element is called point group, and each point group has its own symbol. Or we need a way to designate the point group. Schönflies system is adopted, and we call that Schönflies symbol. Let's have a particular example of methane. So here is a methane molecule, one carbon atom at the center and 4 hydrogen atoms there. So let me bring up some animation so that we may look at those. Okay, so here is the kind of methane molecule from the top view. So there are 4 equivalent C3 axes. C3 means one rotation 360 degree. There are 3 times of the same positions or same conformations you can observe. So for example, this is from the top view. You are looking from above the molecule. So you have this hydrogen near to you, and then 3 hydrogen atoms from you, further from you. There is a carbon atom at the back of this hydrogen atom. So this is a C3 axis. This is one C3 axis. So from this axis, you can rotate. Rotate. Okay, so you see this is a C3 axis, and then you can rotate from this position to that position, and again one more rotation 120 degree goes to this, and another 120 degree goes to this. Okay, so this is one C3 axis, but you have 1 axis, 2 axes for each hydrogen atom, 3 axes and 4 axes there. So there are 4 equivalent hydrogen, 4 equivalent C3 axes, and then also there are 3 equivalent C2 axes, which means that 180 degree rotation. For example, you are looking at bisecting this HCH angle. So from the top of this, so from this direction, you look at the carbon atom, and then you rotate 180 degree to switch this hydrogen to that hydrogen. So this is a C2 axis, and there are 3 equivalent C2 axes. One is this one, and the other one is this one, and I'm not sure I used this one. Okay, there is another one like this one. So each bisecting HCH angle, there is a C2 axis. So there are 3 equivalent C2 axes. Now, up to now, we have gone through 4 equivalent C3 axis and 3 equivalent to C2 axis. And also, for example, we looked at this angle. Okay, so from the top, you see this is one H, another H. HCH has a plane. So this plane, around about this plane, there is a symmetry of this hydrogen and the other hydrogen, and also this plane there is a symmetry, and also that plane has a symmetry. So one hydrogen atom here, there are 3 planes. Sigma, we call that symmetry plane as sigma plane, and then the sigma plane, so 1, 2, 3, and if you rotate it, have this one, and you have, well, this one you already counted, so 1, 2 more sigma plane. And also if you rotate the other way, and probably this one is another sigma plane. So you have 6 sigma plane. In particular, this sigma plane is diagonal sigma plane. So name this sigma D. Anyhow, there is this is a sigma, not S, sigma D plane. Okay, so this carbon, so methane molecule has these 4 C3 axis and 3 C2 axis and 6 sigma D planes. So this is a group of symmetry element that belongs to this, that describe methane molecule or symmetry of the methane molecule. So basically most of the molecule, there are exceptions, but most of the, all molecules, I would say, because there is one particular symmetry element all molecule have. So all molecule have some symmetry. So each molecule have a group of symmetry elements. So let's kind of define some terms before we go further. So there are symmetry element, and each symmetry element we can operate that element to the molecule. Then there is you don't notice any change because you are switching the position of atoms to its equivalent geometrical place. So symmetry element is a geometrical entity such as line, which is symmetry axis, middle plane, which is plane, and a point, a kind of inversion center like that. Those are symmetry element. For methane molecule, we cover C2, C3, and sigma. So basically a line, 2 lines, many lines actually, and 2 kinds of lines, and one plane. Those are symmetry element. And symmetry operation is just move the molecule about a symmetry element so that the orientation and the position of the molecule before and after the operation are just indistinguishable. Okay, so same, just you don't notice any change. Okay, and point group. All symmetry element of a molecule pass through a common point, just to share a point. For example, for the methane molecule, all symmetry element either is C3 axis or C2 axis or sigma D plane, all share a common point, one single point, which is the carbon atom. In that case, center of symmetry, center of a molecule. In that case, the symmetry of molecule is referred to as making a point group, or those symmetry elements are point group symmetry. And so each that kind of group of symmetry element is group. We call that point group. And then point group has a notation to designate what it is. So designation of the point group, we call that Schönflies symbol, because we are following the Schönflies system or Schönflies notation. Okay, so these are symmetry operations or symmetry element. So there are symbols for the symmetry element. We already have seen the C and sigma. I, which is an inversion center or center of symmetry or inversion center. The operation for I is, or inversion center, is the projection through a center of symmetry of a molecule. In the case of methane, there's a carbon atom. There is no inversion center in the carbon atom because inversion symmetry works in such a way that you start from a atom, one position, and go to the center of symmetry, and then exactly the same amount or equal distance on the other side, onto the other side, and find the same atom, same kind of atom. Then that is the inversion center or center of symmetry. That's a symbol I, a symmetry element. Okay. C is a proper rotation axis, and S is improper rotation axis, which are different. But Cn is proper rotation axis, is symmetry axis. The line of symmetry. So they say counterclockwise, but I used to do it in a clockwise rotation. But either way, you just keep the same way. So clockwise, counterclockwise rotation about Cn axis. Cn axis meaning is that 100 and no, I'm sorry, 360 degree or 2 pi radian. So if the Cn means that for 360 degree rotation, there are n times of the same conformation. So C3 means that you'll find 3 times of the same 3 times of the same conformation. So 2 pi divided by 3 or 360 divided by 3 meaning it's the 120 degree. Each 120 degree of rotation, you will find the same conformation. That's C3 axis we have seen in the with the carbon methane molecule. So that's proper rotation axis C3. So Cn is n times. You will observe the same orientation of the molecule, or 360 divided by n. That many degree rotation, you will find the same conformation. And then sigma is the symmetry plane. So reflection across the plane of symmetry, you will find the same atom. Okay, so there are several of 3 different symmetry plane. One we just have seen with the methane molecule, which is sigma d, and there are 2. We'll find out what those are in the next slide. Okay, Sn, improper rotation axis, which has 2 compound symmetry operation. Actually, Cn operation, and there is a perpendicular to the Cn axis reflection. So we call this in other way rotation reflection axis or alternating axis. Those are the same term. Designate this Sn or improper rotation. So it's a counterclockwise rotation about Sn axis by 2 pi over n, followed up to here is just the same as Cn, and then followed by a reflection in a plane perpendicular to the axis of rotation. So it has 2, such as Cn and then sigma h. Okay, sigma h is the horizontal mirror plane, which is perpendicular to the axis of rotation. So these are compound symmetry operation of Cn and sigma h. So that is improper rotation axis. And this is very intrinsic or peculiar thing about the symmetry operation. Identity element, all molecule has this operation because it just leave it alone. The operation that leaves the system unchanged, just same as it is. So that's E operation. For the group of symmetry element, we need this one. So identity element, we call the symmetry element, and or identity operation, just to leave it alone. So that symbol is E. So these are inversion center, proper rotation axis, symmetry plane, and improper rotation axis, and identity are symmetry element, 5 different kinds, and then these are the symbols for that, and then it describe the operation is described in the 3rd column. Okay, so we'll just look closely how the rotation or the symmetry element or operation works here. You just there is a small dot here. Okay. So Cn, in this case, we are describing C2 rotation. So C2 means that n is 2. So 360 divided by 2, which is 180 degree or pi. Okay. So this is a kind of water molecule. Okay. So one oxygen, the green hydrogen here, green hydrogen. Okay. So C2 axis bisecting HOH angle. Okay, so this is C2 axis, and then if you rotate one C2 operation, so this dot goes, so one C, okay, here is the C2 kind of graphical symbol for the C2 rotation. This is it, and then if you do C2 rotation, C2 operation, 180 degree rotation, this dot moves to here. Okay. So this is twofold axis of rotation, in other kind of verbally. So this is symmetry, C2 symmetry element. And in this case, this is just one operation or rotation. symmetry here. So that C2 axis is the principal axis of rotation. Actually, if there are many rotational axes there are, if there are many several axis of rotation, then highest n, the largest n, the rotation with the highest n is the principal axis of rotation. In this case, there is just one, so C2 is the principal axis of the rotation for water molecule. And then let's see, this is let's say this is ammonia. Okay, then for ammonia you have one C3 rotation operation with 120 degree, so this dot moves here, and another C3 rotation that moves to here. Okay, so one C3 operation, another C3 operation. Notice that this is a clockwise way of rotation, but definition was counterclockwise. Either way, that's fine. And maybe that is relevant to your kind of actually the symmetry operation is a applying operator to a molecule. That operator could be represented by a matrix. In the case that sign might be better, but in this case you just graphically you are just doing 100 degree rotation clockwise in this case, and another 120 degree rotation. Okay, so one C3 operation, another C3 operation. So first operation is C3 and this is double, so C3 square, and which is actually reverse C3 operation. Here I designated C3 minus 1 inverse. Okay, and if you do 3 times, well, 1, 2, 3 times, then you will go back, you'll be back to the same original position. That's just leave it the same as the leave it alone, which means that identity operation. So ammonia has C3 symmetry axis, which that symmetry axis is actually contains one C3 and one C32 or C3 minus 1 and identity. Okay, 3 operations in C3 operation. Okay, now we are looking at the reflection operation or symmetry plane. So in that case, we back to water molecule. So okay, for example, it has C2 axis. So if it operate C2 operation, it goes this way. Okay, so let's follow the dot for a while. And but HOH, this angle, bisecting this angle, there is a C2 axis, and then there is a plane just bisecting the this angle. This we call sigma vertical plane, so sigma V plane. So if you reflect against this sigma V plane, this dot moves that there. Okay, so sigma V middle plane includes the principal axis of rotation C2. So, but there is another sigma V vertical middle plane which also include the C2 axis. But in that case, in this case, that sigma vertical symmetry plane include all molecule, all atoms, HOH. So if you reflect against sigma V, okay, we have already sigma V, so we tell or differentiate this sigma V plane as sigma V prime. So if we reflect against sigma V prime, then there is no change in the position of atoms. So that still remains here. Okay, so that is sigma V prime reflection. But so it does not, it does look unchanged. Okay, so basically that we just looked at sigma V vertical middle plane, and then there are 3 different middle planes. Sigma V is, well, let's look at this as a kind of a benzene molecule. So each apex there are carbon atoms, and this is C3 axis. Usually we put some like a hexagon here. to designate the C3 axis, C6 axis, and then sigma vertical usually most of the time include the atom. So C atom, this called we say vertical mirror plane, and this is sigma D, diagonal mirror plane, the green one here. In this case, that goes between the atoms, so that's diagonal mirror plane. So, and also sigma H we just have seen with in conjunction with SN operation. So there is this is an rotation axis perpendicular to this rotation axis, in this case C6. There is a plane that is sigma H perpendicular to the axis of rotation that we call horizontal mirror plane. So there are three kinds of mirror plane: vertical, diagonal, and horizontal. The symbol for that is sigma V, sigma D, sigma H. Basically, sigma is mirror plane. And now we will go for inversion rotation or center of symmetry. Okay, so here we have a molecule, let's say SF6, something like that, and at the center, in this case S, if that's SF6, it's S atom, it's the inversion center or center of mass, yeah, inversion center of the molecule. So so let's say for atom number 1, go to the center of inversion, and then it's the same distance to the other side, you'll find the same atom. So basically the inversion rotation is just a flip 1 and 6 position, and 2 and 4 position, and 3 and 5 positions. So inversion operation projects each atom through the center of inversion and across to the other side of the molecule. So that is inversion operation, and this is then we call center of symmetry or inversion center, the same term. And then the improper rotation. So it's a rotation and reflection through the plane perpendicular to the axis. So we have seen this one as S4 with methane molecule. So that's rotation reflection or improper axis. So in this case, A, B, C, D, we just kind of differentiate each hydrogen atoms here. So one C4 rotation meaning is basically C4 is 360 divided by 4, 90-degree rotation. So 90-degree rotation, A goes to the A goes A was here, and then it goes there, and B goes the other side. Well, okay, and then D goes up, C goes down, something like this. Okay, just like this. And then this is C4 rotation, and then perpendicular to the C4 axis, there is a sigma H horizontal plane. So mirror plane mirrored back, B to the this side, A to the other side, C the other side, D the other side. So this way. So this is C4 followed by sigma H operation, that is C4 sigma H S4. That's improper axis of rotation. So you will see S4 operation from this orientation or this conformation to that conformation. So sigma S4 is basically C4 and sigma H rotation. What actually we have done is sigma H C4 in this case. So the operator to the operand, the closed one, acts first. Okay. So if you do twice S4 twice, meaning is that one and another one goes back. Really? Okay. Then that's C2. A goes here, and then B goes up. Okay, so that is the way it is done. Then the C2 rotation. And if you do 4 times, then you have identical back to this position. C2 twice, that's the way, that's how it does. And also 3 times is just a S4 inverse. So these are just the relationship of S4 operation. And improper rotation, you can notice that this is ethane molecule. So there is S6 axis here from one carbon to the next carbon. So this is a staggered conformation. So if you do one C6 operation, then you will do 60-degree rotation. So this one goes to top and then goes down like this, and then middle plane in the middle, perpendicular to C6 axis. Then this goes that, and that goes that, and the other way. So basically what you find is that the same conformation, which find that S6 operation, which is C6 operation, and reflection through the middle plane perpendicular to the C6 axis. Okay, so we looked at the ethane molecule. And basically, I would say that if you have a model, like just a Borenstein model, you will find this you can follow this very permanent, very solidly. Okay, improper rotation. There are some improper rotations which are not possible in a way. So S1 is not possible because S1 is just the same. Well, S1 is 160 rotation, just the same position, and then reflection, which is just as same as that sigma reflection. So S1 does not exist because it's the same as a middle plane. Then we just use middle plane instead, S1, so there is no S1. And S2 works the same way. If you do S2, first to the C2 and reflect, which is just the same as the inversion center. In that case, we use inversion symmetry, not S2 axis of improper, S2 improper axis. All right, so it's a kind of cumulative idea what you have learned, okay, which is that we are looking at benzene molecule C6H6. So benzene molecule you are looking at from the top, and then there is a C6 axis. C6 axis means that 160, I'm sorry, 360 divided by 6, which is 60 rotation, 60-degree rotation. Each 60-degree rotation, you'll find the same conformation. You don't see any change in its shape. So C6 rotation operation is once. Twice is actually the same, 1, 2, the same as C3 operation. 3 times of C6 is C2 operation. Okay, if you do 4 times, that's twice of C3, and 5 times, which is 1 reverse. Okay, so basically C6, 5. Okay, and if you do 6 times, that's the same as identity operation. So in this C6 symmetry element, you have 2 C6, this one and that one, C6-1 and C6-5, and then 2 C3, C6-2 and C6-4, which are C3 and C3-2, and one C2, which is C6-3. Okay? So basically for this C6 rotation, you have 2 C6 and 2 C3 and C2 and E, which are all included in the C6 axis. And then there are this C2 axis of rotation is in the plane itself, of the molecular plane, I mean. So C2, one C2 here, and another C2 there, another C2 there. So 3 C2s. But you have C2 here, okay? So that one is C2 prime. And between the atoms, in that case, one C2 and another C2 and another C2. 3 C2, but you have C2, C2 prime. This one is C2 double prime. And also, of course, there is an inversion center at the center of the molecule. And also, for that matter, each, for example, this one has horizontal mirror plane. There is a horizontal mirror plane. Then you will expect that 2s3, 2s6, okay, horizontal mirror plane, of course. And then we have seen this sigma d and sigma v in the previous. So sigma 3 sigma d mirror plane and sigma v mirror planes. Okay, so those. Okay, so these are symmetry elements of benzene molecule C6H6. Okay, so all these symmetry elements share the common point, which is the center of the molecule in this case. And then, so this we call a point group. And the symbol for this point group is D6H. And I'll show you, we'll talk about how we obtain, how we get this symbol. This symbol is called Schönflies Symbol, or because we are following the Schönflies system, or systematic way of finding the symmetry symbol, I mean a point group symbol. Okay, before we go further, well, actually the second lecture of this series, symmetry series, about the group theory. And then before we jump into the group theory, let's define what is group. So what is group of symmetry element in this case? And the operation, well, firstly, we found number of symmetry operation or symmetry element for some molecule. Previously, just before, we did that for benzene molecule. And then those group, we can call that as a group of symmetry elements because of these 1, 2, 3, 4, these properties of the group. So operation that correspond to successive operation of two members of the group. Okay, so let's say C6 operation and C2 operation, something like that. And pick up any two symmetry element of the group and then operate one by one, twice in that case, two members, two operations. Then you'll find equivalent operation of a member of the group. So meaning is that the operation that correspond to successive operation of two members of the group must be a member of the group. Okay? The same operation from one single member. This is also applies to scale operation, meaning is that if you do C6 operation twice for the benzene molecule, you do C6 once and another C6, which is C3 operation. There you must have C3 operation in the benzene group because you have applied two C6 operation. There must be one symmetry operation that correspond to that two C6 operation, which is C3 operation. This is a kind of relationship among the members of the group. And also there must be identity operation, E. Must be a member of the group. So we had E, which was 6 times of C6 operation. Anyhow, E must be there, identity operation or identity element. And number 3, the operation must be associative, meaning is that if you do 3 operation, you do one operation first and then AB operation first and apply that operation to the next to C operation, or you do BC operation and then A operation, something like just like this. So this is a associative relationship. So symmetry operation must be associative, or member of a group must be associative, but they do not have to be commutative. That's what it says. And also each operation must have unique inverse, meaning is that every member of the group must have its own inverse. Inverse meaning is that if you do A operation and A minus operation back to the same position, meaning is that identity element. So AA minus 1 is equal to A minus 1A, which is equal to identity. So okay, so that's basically 4 properties must be satisfied for a group. So Schönflies developed a point group of symmetry operation which left one point, so usually center of molecule, in molecule unchanged. So it is useful to classify the molecule according to their point group. So for example, we did that, we collect all symmetry element for benzene, and then we designate that group as the 6H, just like that. So that D6H kind of like that symbol, group symbol, is the Schönflies symbol. Okay, so what group is good for? For example, we have water molecule. So water molecule has C2 symmetry element and sigma V prime and sigma symmetry element. Okay, so and also there is always E operation there. So C2 sigma V and sigma V prime. You just know this include all this sigma V prime plane. That sigma V plane include all atoms, and this is just a bisecting HOH angle. Maybe you can define the other way, but this is the way you define in this case. And then this makes a group, and that group symbol is C2V. So C2V's group is for water molecule, all water molecules symmetry element. And then you can make a multiplication table for the group. So this E identity operation must be there because you want to make this multiplication table for the group C for any symmetry group. You remember the first rule is that any two member of the group operation yields the result identical to one member of the same group. So if you do C2 twice, then there must be the equivalent. C2 twice meaning is that you get back to original position, which is the identical as it is, and then that is E operation. So 2 C2 operation is, there must be something which is E. So that's why you need identity operation, identity element always for a group or for a molecule. So E twice, once, twice, E, same as. For example, we just did C2 and C2, which is E. Okay, if you do C2, this goes to that, and sigma V. Okay, this goes to there. Okay, so let's follow this laser pointer. So if you do C2 operation, okay, it was here, and then sigma V back, which is actually the same as E, but if you do sigma V prime operation, which it was here, and then just the same. So actually C2 and sigma V prime is the same. So C2 sigma V is sigma V prime. Okay, this is the way we construct this multiplication table. Okay, for any symmetry group. So for a symmetry group, we can construct this kind of the same way as we did a multiplication table of among symmetry elements or symmetry operations. So first you do this one, and then one of these elements from the row, and then this column, following this column, and then the result is this. So this we call the multiplication table. From this multiplication table, or the relationship from here, we develop the character table in the next probably next lecture. Okay, CNV point group. Okay, CNV is that something like C2V we just did. Okay, C2V for the water molecule. And this one is, for example, ammonia, which has C3 axis. Then this is C3B. Okay, so C and V point group, water and ammonia both belong to C and V because C2 and C3, and then there is a vertical middle plane. So what it has is ammonia 1 water belongs to C and V class of molecules because there are vertical planes of reflection about that includes the axis of rotation. In this case, C2, and that's in this case C3. And okay, that's it. But there is no horizontal plane. If there is a horizontal plane, then that's different one. Okay, so C and B point group all have CN axis and vertical middle plane. Okay, DNH in this case that has horizontal middle plane. So DNH group has horizontal middle plane. So and also axis of rotation. Okay, so this is D4H. We'll see how it. Well, we looked at D6H before with the benzene molecule. Okay, but there are special cases or special point groups. If that the molecule is linear, like H2, HCl, N2, like that, linear molecule is C sigma V or D sigma V. For example, H2, which has horizontal middle plane, horizontal against the molecular axis, horizontal middle plane there. Those are D sigma V. But HCl, it does not have middle plane. In that case, that's sigma infinite V. There are infinitely many sigma vertical middle plane. That's what it says. And the one we did, our first example of molecular symmetry was methane, and that's actually a special case, which is TD, tetrahedral molecule or tetrahedral symmetry. And also, if there is cubic symmetry, cubane is a molecule, but it's not really popular case, but very rare. But that point group is TH, cubic symmetry, and octahedral, which we have seen just before, a SF6, something like that. That's OH, octahedral molecule. And also icosahedron, which has 20 faces, and dodecahedron, which has 12 faces. In the case, that symmetry is IH. And what we have here is actually Buckminster fluorine. Buckminster fluorine is, I think that this is icosahedron. I think, yeah. So Buckminster fluorine has these many I15, C5, 12, C5-2, 20, C5-3, 15, C2, inversion, 12S10, 12S10-3, 12S6, and 15 sigma. So there are 120 symmetry operation. For particular thing, this one is IH symmetry. And also, a special case for symmetry is a sphere. Atom is considered to be a sphere. So spherical symmetry is designated by KH symmetry. These are all Schönflies symbols in various kind of special point group. Okay, so now we are here now at last. How we designate or find the Schönflies symbol for the group of symmetry operation found for the molecule. So if you have a molecule and list down all symmetry elements you find for the molecule uniquely, not repeating. Okay, so symmetry element you found for the molecule, and then if you look at this molecule, and then if that's linear, yes, then go this way, and then if there is a inversion center, if yes, that's the H symmetry. This is the infinite H. And if that's linear and then there is no inversion center, then sigma infinite H group. Okay, you just found these are special case. Actually, this is all these are special cases just we have seen in the previous slide. And then if that's not linear, okay, and then if there are 2 or more Cn n greater than 2, meaning it's a C3 or C4 or C5 or C6 like that, 2 or more, yes, then it could be a special case. And then if there is an inversion center, yes, and if there's a C5 symmetry there, yes, then that's IH, and if not, that's OH. And there was no inversion center, then that's tetrahedral. So you'd basically find all these special cases from this flowchart. Okay, then there is a unique Cn, n is greater than 2. That's okay. The greatest number of n will designate the principal axis of symmetry. So if there is a principal axis of symmetry which is with n greater than 2, then you are having a kind of regular molecule, not a special case. And then if there are Cn, yes, if there is a Cn, for example, greater than 3, greater than 2, if there is a Cn axis or not. If not, if there is a sigma plane, if yes, then the CS symmetry, okay, which is okay. And then if there is a inversion center, that's C1. C1 is just the same as identity. There is no symmetry, which actually it is, except that identity operation. And if there is a yes, that's yes case, and no case, there is a C1. That's it. And if there is no inversion center, that's C1 identity. And if there is inversion center, that's CI. These CSC1 CI, CSCI C1 is a special case for other special cases, which is very less symmetry. Okay, and then if there is a Cn axis of rotation, and then it asks that if there are n C2 axis perpendicular to Cn, if yes, and then there is if there is a sigma H plane, then D and H case. If not, if there is sigma D, yes, that's D and D, and then not, then that's Dn. So these are the D Schönflies symbols. And then now, if there is no NC2 perpendicular to Cn, no, then if there is sigma H, yes, then that's sigma C and H. And then if there is sigma V, then that's sigma NB. And then if there's S2n axis there, then S2n. If not, that's Cn. For example, you remember that for water molecule, which has C2, sigma V prime, and E operation. So we start here. Is linear? No. Then if there's 2 or more Cn, we have just one Cn. Okay, greater than? Oh no. So we go here. If that Cn is there, yes, we have Cn. And then if there is a perpendicular to Cn, C2 in this case, but we have just one C2, there is no such. And then we are here. And then if there is a sigma H, no, we have just a sigma vertical. Yes, we have a vertical. Then that's C and V, which is C2B in this case. So water molecule has symmetry element C2, sigma B, sigma V prime, and E. Those are symmetry element of a group of symmetry. That symmetry group is C2B in this case. So okay, so let's end the first lecture of symmetry, and then there will be 2 more lectures for the molecular symmetry. Thank you for listening, and then enjoy your symmetry of molecules.